So welcome back to the lecture series of communication system. In this lecture, it is a basically continuation of our previous lecture of angle modulation. So in previous lecture, we see what is the definition of the angle modulation, then what are the different parameters, for example, expression for FM, expression for the PM, modulation index, and then the definition. Again, they have effects of the FM on the phase or the frequency of the carrier signal. Then it is again the continuation, what are the dependency of the frequency deviation on the amplitude of the signal, and then the frequency deviation for the frequency of the signal. Then we have discussed about the relationship between frequency and phase modulation. Then we see the spectrum of the FM and PM. This particular diagram, just I try to explain what are the spectrum behind the AM and FM. See this particular A, it is our modulating signal or message signal. So and then B is our modulating signal or message signal, A is our carrier signal. So see in the B, our carrier frequency is varies in accordance with the amplitude of the message signal. So first we fix the sum of terms in the message signal, for example maximum slope, then the maximum deviation, then it's zero crossing, and then it is the maximum. So we put some marker to show what are the maximum slope, what are the zero crossing, what are the zero slope. Then our modulated signal, so C actually represents the frequency modulated signal. So see this particular, compare C and A. So we find there are the change, we got the slight change at this point. Then we got slight change at this point. If you see here, we got the slight change. Similarly, if we see at the maximum slope point, see this particular diagram, this, it is a expanded version. This if you compare this particular part and this part, it is the expanded version of this. So it's so basically frequency variation. See here the maximum deviation at the negative side. Again it is the compressed version of the carrier. So this particular part show the modulation. Similarly here, if we see this maximum slope, so here again it is expanded version of the carrier. Here it is got the compressed version of the carrier. So in this way, this particular waveform is called the FM. But in the case of the PM, maximum change we got at the point of the zero crossing. See here it is a zero crossing point. So see here the zero crossing point, there are changes. Similarly see here, it is a zero crossing point, then we see the some change. So here it is a zero crossing point, there are some change. Again this is a zero crossing, then we got some change. It means in the case of the PM, frequency variation or the variation in the waveform is observed at the zero crossing, because the phase it changes at the zero crossing. Actually in the zero crossing phase it changes, but in the case of the FM, there are the frequency variation, not the phase variation, that can be observed where the slope is maxima or minima, or the slope is maximum in the positive direction and the maximum in the negative direction. So at that way we are able to identify FM and PM. But if we remove the carrier part and modulating part, then we are not able to identify which is the FM waveform, which is the PM waveform. Both is look like a similar type of the waveform. So these are the basically similarity between FM and PM waveforms. It means to clearly identify FM and PM waveform, we need to draw carrier, then the modulating, then we mark the point of the maximum slope, minimum slope and zero crossing. Then we draw FM and PM. Then we are able to identify which waveform is FM, which waveform is PM. But once we remove the references, we are not able to identify PM and FM separately. Then FM is divided into the two parts, narrow band FM and wide band FM. We see I already explained that modulation index is represented by the beta. If the in the case of the AM signal, beta is small, but in the case of the FM, if the beta is small, it is called narrow band FM. See this particular equation for a narrow band FM. If you compare this equation with the AM equation, so only there are a slight change at this particular point. All parameters are same. So here we got the negative, here we got the positive. Otherwise, a narrow band FM is just like a AM signal. And if you see the phasor diagram of this, so this particular axis sinusoid sine, and it is a minus cos. So that is our resultant FM output. It is our VC, and this is the आपका, that is also called VC. So in this way we can draw a spectrum of a narrow band FM. Similarly, in the wide band FM, beta is greater than 1, that is nearly approximately equal to the 10. Then we use the Bessel's function to solve our FM signal, FM waveforms, FM equations. That is the Bessel's function is given. J0 is the Bessel's function of the basically 0th order. This is the Bessel function of the first order. See this particular explanation. So the Jn is a Bessel function. So the spectrum is composed of the carrier with amplitude J0 beta, and there are a sideband. So that is our carrier J0. All other are the sideband, and its sideband is centered around omega m, twice omega and thrice omega. See this particular expression, it is very clear. So unlike AM, FM has an infinite number of the sideband along with the carrier. These sideband are separated by the frequency FM, 2FM, 3FM, and so on. So these are all about the wideband FM. That is the graphical representation of the Bessel's function of J n beta. So they are the different value of the n. So it is J0, J1, J2, J3. So this graph is plotted, and on the basis of this graph we are able to got the value of the J0, J1, J2, and so on. Then these are the values of the Bessel function, beta equal to 0.1 for n equal to 0. So these are the basically value, and this value has single and double side underline indicate the number of the harmonics containing 70%, 98% of the total power. So these actually they are discussed about this 70% and 98% of the total powers. Then the bandwidth for a wideband FM case, it is the twice delta F plus FM, that is called the bandwidth. That in this particular bandwidth is calculated by using the Carson formula. For low modulation, in the case of the narrow band FM, delta F is very small in comparison to the FM, so the bandwidth is equal to twice FM, that is similar to the bandwidth of the AM signal. And these are the power. PT is the basically average power contained in the side bands. So these are representing the power. Then that is the expression for the sinusoidal FM signal. These are the Kp EMT equal to Kp Em sin omega t. That expression is already explained in the first lectures. In the previous slides I am already explained. Just take the second term that shows the modulation. And then they try to prove that it is directly proportional to the peak modulating power, or just our purpose, but actual expression of FM signal is given in the previous slide. That is the actual expression, but the first term is the carrier sum. So here we remove this carrier term, and so that it is directly proportional to the peak modulating signal. These are again the phasor representation of the wideband FM. See here with the reference line, one is the frequency variation, in the second the phase phi is varying. Then FM generation, the first FM can be generated by the vector diode modulator. Then we use the reactance modulator. Then we use the linear ICs to generate the FM, and there are indirect vector, which means first we generate narrowband FM, then we convert the narrowband to the wideband FM. Similarly, in the PM generation, we use vector diode and direct method with transistor. There are the two techniques, and similarly here there are 4 techniques to generate the FM, 2 techniques to generation of the PM signal. Then the advantage, it is a superior immunity to the noise. Then immunity can be achieved because the interfering signal from the same frequency are rejected. FM signal have the constant amplitude, and there is no need to use linear amplifier to increase the power level. So these are the advantages. Similarly, disadvantage, it required more spectrum, it required more complex circuitry. So in the past, circuit used for frequency modulation and demarcation involved very complex. The proliferation of ICs, complex circuitry used in FM, has all but disappeared. IC are inexpensive. It means nowadays basically we have ICs are inexpensive, so we are able to use it, and it is not a disadvantage. Nowadays, FM is not a disadvantage. So these disadvantages are removed. For example, the expensive ICs. ICs are not expensive, so its circuit cost will reduce, and it's have the excellent noise immunity. So FM is nowadays more popular in comparison to the AM. So see here, there are the advantage. AM broadcasting is used, then FM broadcast, FM used, stereo multiplex sound, DSB AM or FM is used, TV sound, FM is used, TV picture, either AM or VSB used. These are the basically different applications where FM and AM are used. And it is also clear that FM is there is a major application of FM in comparison to the AM. So these are the basically transmitter and receiver, so that will be discussed in the next lecture. So that's all about the today lecture. Thanks for your kind attention.